I'd like to talk to you about number 45. Number 45 says, find a simple basic function that is a right-end behavior model and a simple basic function as a left-end behavior model for the function. So we want to find a function that will explain the behavior at the end as we go towards infinity. So when we talk about a left-end behavior model, we're talking about going to the left and seeing what's happening at the end as we approach negative infinity. And when we talk about a right-end behavior model, we're talking about what's going to happen with the behavior at the end as it goes to the right. So maybe we should call it the end behavior model of the right, which would be going towards infinity. Alright, well, we're going to pick a function. We want to pick a function that is going to give us the limit at x approaches infinity is equal to 1. If you look at the definition on page 74, it says that for the right-end behavior model, we're going to plug in infinity, and if f of x over g of x is equal to 1 as we approach infinity, then that is a right-end behavior model, that function, g of x. And if, when I plug in negative infinity into f of x over g of x and I get 1, then I'm going to have the left-end behavior model. I'm going to have what is happening at the end of the model as we go to negative infinity. And I just hope this will be clear, because whenever I say right-end behavior model, I think that doesn't make sense. But if I say the end of the behavior of the function when you go to the right, that makes better sense. And the end behavior of the function as we go to the left, that makes sense. So you're going to plug in negative infinity. So let's have a look at this equation. And A is asking us to find the right-end behavior model. So we want to plug something in, we want to find something that we're going to divide this function by. That will be my g of x that is going to make this function go to 1 when I take the limit as x approaches infinity. So I want the function to go to 1. So I'm going to pick a value that is going to help me reach my goal of getting 1 as I take the limit. So if I divide this equation by e of x, then when I simplify that, I'm going to get 1 minus 2x over e of x. And what happens here is as we take the limit as x approaches infinity of 1 minus 2x over e of x, when I plug in infinity, take the limit, I'm going to get 1 plus and then 2x over e of x. Notice as I plug in infinity, the bottom is going to grow bigger than the top. The bottom is going to blow up because e to the x is an exponential function that grows quickly, and so it's going to go really big. And so as this number down here is getting bigger, we're getting closer and closer to 0. The number is going to get smaller and smaller and smaller as the denominator gets bigger, bigger, bigger. So this is 1 plus 0, so my limit as x approaches infinity is 1. Therefore, this equation right here is a right-end behavior model for this function that we started out with. This e to the x minus 2x. Now we need to find something that will be a left-end behavior model, and we're going to plug in infinity, negative infinity this time, and let me get my eraser to stop and my pen to mark. Okay, now we're going to pick a value. Now, if we use that same value that we used a while ago, when I plug in negative infinity, the number is going to get really big. If I use e to the x again, and you could try it and see what happens, but if I use that, I'm going to get e to the negative x, or e to the negative infinity in the denominator, and that's actually going to be a really small number, and so, which is going to be going to 0 on the bottom, but then the number on top is going to, but not actually get there, and the number on top is going to be getting bigger, so it's actually going to not have a limit. It's not going to go to 1. So I don't want to use e to the x as my left-handed limit because I'm plugging in negative infinity. Okay, so let's try something here. This time we're going to divide it by negative 2x, and you're going to kind of see a little pattern in these, and you get e to the x over negative 2x minus, actually negative make a plus 1. So if I take the limit as x approaches negative infinity this time, because I'm doing the left end behavior model, and when I plug in, I'm going to get 1 here because the limit of 1 is 1, but on the top, if I put a negative infinity on top, that number is going to get really small. So the number is going to get really small on top, and on the bottom the number is going to get really big. So this number is going to be approaching 0, and this number is going to be growing, but it's going to 0. Even though the denominator is getting bigger, the top number is going to 0. So it's 0 plus 1. That's what happens when you plug in negative infinity. So therefore, since we get 1 when we take the negative limit to negative infinity, then it is a left-end behavior model. So let me erase, make some room to write my answer. So negative 2x would be an equation that would represent what happens on the left when you plug in negative infinity. So it's a left-end behavior model for the original function, e to the x minus 2x. Well, I hope that helps, and hopefully whenever you work through the other problems, this will become clear.